Our next presenter is Uzma Tahir. She is from the Biological Sciences program at Northern Arizona University, and her major professor is Dr. Kiisa Nishikawa. The title of Uzma's presentation is Emulating Biological Movement Using a Robotic Prosthesis.
Imagine a cheetah running across the savannah. A cheetah can run up to 75 miles per hour on a surface that is grassy, has rocks, roots, and maybe even some hiding ditches. The cheetah, however, rarely trips while traveling across this very complicated terrain. And at the top speed of the cheetah, there's not enough time for the brain to micromanage each step or misstep that might occur. To overcome this, our muscles have evolved ways to respond to sudden changes in the environment automatically without our brains. For my dissertation, I am studying how our muscles manage to be faster than our brains. I then take those resulting biological principles and apply them to the control of a robotic prosthesis. Most people in the United States with an amputation below the knee use a carbon fiber foot that is designed to store and release energy like a spring. Our muscles, however, are more like motors. They provide a lot of power and work to help move us forward. People using a prosthesis that can't compensate for those missing muscles find it much more difficult to travel across their environment. The biome, pictured on the left, is a robotic prosthesis. It has a motor and a battery system built into it that is designed to help provide this power. However, now you have to decide exactly when and how much power to provide. We decided to take a biological approach and designed and implemented a controller based on neuromuscular principles of movement into the control software of the biome. We then asked an individual with an amputation to come in and test out our model. While he walked on level ground and walked upstairs, we were able to measure the forces at the ankle joint using the internal sensors of the biome. On the left, we have a sample force profile of the ankle joint of an individual walking on level ground using their intact biological ankle. Using our neuromuscular controller, we were able to recreate the forces at the ankle joint. We then asked him to transition to walking upstairs, and once again, we were able to provide power in a biologically relevant manner that allowed him to successfully ascend stairs. Our controller is the first of its kind that is able to transition from level ground walking to stair ascent without changing anything about how the controller works. In fact, our volunteer tells us that using the robotic prosthesis has allowed him for the first time to walk upstairs fast enough to get out of breath. My projects have the potential to transform our fundamental understanding of how muscles work while improving the quality of life for people with an amputation who can now travel across their very complicated environments just like the cheetah. Thank you.